Okay, hello everybody. So welcome to this lecture series on linear systems theory. So we continue with the week 4's lectures on what we call as solutions to the state space equations, and we coined the term called the state transition matrix earlier in this week's lectures. So we just continue around that or answering those questions, and specifically in today's lecture we will focus on linear time varying systems. What was the advantage in the time invariant case was that we had nice looking closed form expressions, that a matrix exponential e power at was essentially the state transition matrix, and the properties were easy to infer and even derive. So let's first just do a little example before we warm up towards the general case. So I'll start with a simple example. Let's say I have a time varying system. So essentially I am looking at x dot of t is a t a t x t plus b of t u t. So that's the difference is that this matrices A, B also now vary with time. Okay, so as a little example, so let's say I have a system which is x1t, x2t varying in the following way: 0, 0, t, 0, and x1 of t, x2 of t, and let us assume for the moment that u is equal to 0 and I am actually looking at an autonomous system. Okay, how would the solution of this look like? Okay, if I write down the first equation, that will be x1 dot of t is 0, and let me assume some initial conditions at x1 at 0 and x2 at 0. This could be given by x1 0 and x2 0. Okay, so this is easy to solve, that the solution x1t will be x10 for all times t greater than or equal to 0. Okay, so the second equation now. So I have x2 dot is t times x1t plus 0. Okay, now what is x1t? X1t is simply this for all times. So this t x10, sorry. Okay. Now x2 of t would just be the integral of this, right. So integral 0 to t tau x1 naught d tau, and this will be equal to half t1 square x1 naught plus x2 at 0. Okay, that's a simple looking equation I can solve easily, and let me just check for what if my initial condition is 1 comma 2. The solution would be x of t is 1, okay, and then here I will have so x2 naught is 2 plus x1 naught is 1, so I will have 1 over 2 t square. Okay, it's not a t1, just a t here. Okay, so that's in general. So we are again looking at integrating the differential equation. Okay, so so these are the equations that we will be interested in. X dot is ATX, and all these A, B, C, and D matrices are now changing with time. So the question again is the same, right? So given this set of equations with a certain initial conditions, how do we find x of t for all times t greater than or equal to 0? Similar to the LTI, the time invariant case, let's start with a scalar equation or a univariate example. Okay, A is in R, and and then let us start with some initial conditions. The objective is to find x of t for all times t greater than or equal to 0. Okay, so let us take some q from the LTI systems and say we will add some kind of an exponential solution at e power a t times x0. Now, let me propose a solution which is like this. Okay. Now, what I would want to verify is this the solution, right. So, first is so it should satisfy two things, right, as said yesterday or in the earlier lectures, that it should satisfy the initial condition that x t is a solution to this differential equation here if it satisfies the initial condition and additionally it satisfies the differential equation too. So, let us see first what is the initial condition, right. So, x of 0 is e power 0 to 0 whatever is in the integral x 0, right. So, the initial condition is like retained. Okay. Now, does it satisfy the original differential equation? Well, again I am talking of the autonomous case where u is equal to 0. So, I just differentiate and then okay. So, all the steps are written down here and actually reconstruct or regain my original differential equation, and therefore, I can claim that the equation labeled 2 is actually a solution to the scalar differential time varying equation. Okay. So, what did we do or how did we extend this to the n dimensional case in the LTI case, right. So, we had x of t is e power a t times x 0 as the solution, and we derived this also as a power series, right. So, if you remember those derivation, and loosely we could kind of extrapolate this to the multivariate case in like as a in a very crude way, saying just replace the small a with capital A and things will work out, and then everything instead of being a scalar is now a vector and the 1 becomes an identity and so on, right. Of course, and we did actually we just did not do it blindly, but we actually verified that this was actually a solution to the vector differential equation by again verifying it with the initial condition and also that this solution actually satisfies the differential equation. Okay. And now, can I just do the same for the time varying case? So, let us start again with this, right. X dot is e power a times t x, where x was of this form. Okay. Now, I can look at this exponentially here, right. I have another exponential which with an integral sign e power a to d a tau d tau. Okay. Now, I can always expand this, right. So, with the formula of the exponential and I get something like this. Okay. Now, I can extrapolate, all right, let me try and extrapolate this to the multivariate case where x dot is a x with x being in R n instead of R. Okay. So, can I just write it directly in this way? So, and also verify if this is true. How do we verify if this is a solution? So, I just try to do this for the vector case and just check if this is actually true. So, again what do I need to verify? I need to verify the initial condition. I also need to verify that this solution actually satisfies the differential equation by just differentiating this x of t. Okay. So, well I just do all the computations, I will skip them, but they are actually written down quite nicely here. So, what we find is that if I just extrapolate this by just replacing small a with a capital A, it turns out that this is actually not the solution, right. So, and then that is essentially because these matrices do not actually commute, right. So, therefore, the solution to the vector differential equation x dot of t is a t x t cannot be directly obtained by extrapolating the scalar or the univariate case. The proof is written down quite well here. So, I will skip reading those steps, but you can just write down for yourself. So, the aim is to show that I just cannot do the crude way of extrapolation that I did in the LTI case, just because I can actually show that this is actually not true. Okay. So, so there are ways to do this and that is called the Pino-Baker formula. It looks a little ugly and complicated, but it's nice to know how people actually ended up building up theory to solve these kind of equations of when there were no tools, how would people actually think about even arriving at solutions. Okay. So, from the univariate case, okay, so this is what we tried doing, right, in the univariate case, right, and this actually does not work, right. So, instead, so let me try doing something like this, right, x of t is identity, this remains the same, and I have some kind of have a double integral, and then I can expand this to have triple integrals and so on. And let me see if I can verify this, right. So, first is it a solution? Well, does it satisfy the initial condition? Well, the answer is yes, because you just integrate everything from 0 to 0 and you retain the initial condition. That is true also in the previous case. In this case, we could retain the initial condition, but the solution did not satisfy the differential equation. Now, I keep doing on all the keep on doing the differentiation and actually see that this satisfies my original differential equation. Again, we have used the Leibniz rule that we used yesterday to verify solutions of systems with inputs, right. So, instead of doing a blind extrapolation, we can do a slightly different kind of extrapolation, or possibly mixed with a bit of intuition to actually find that something like this as a solution can be proposed and can also be verified. Okay, I will again not do all the details of it, you can just write down for yourself. Okay, so to conclude here about the solution, so we say that x of t is given by this solution, right, with it's a lot of integral terms in the middle, and this thing inside the bracket is what I call as the state transition matrix, right, phi at t starting at any initial condition t naught. Okay, so one thing about this, okay, what is this phi? And yesterday or in the previous lectures when we were talking of solutions to even LTI systems, we started also comparing it with the solution to a matrix differential equation, and that was not really obvious of where it actually comes from. So, if I look at this phi, okay, let me check, right. So, what does this phi satisfy? Phi of say t naught, the initial condition would just be the identity, right, because all the integrals would just vanish. Okay. Now, I do what is phi dot of t comma t 0, I differentiate the first term, I get a of t plus all these terms, right. So, so what I can compute, again I skip the computations and they should be easy to follow, that phi of t comma t 0 can be shown to be a of t phi of t comma t 0. Okay. So, this is how we actually derived the matrix differential equation, or how we actually infer that the solutions actually can be interpreted as coming from a matrix differential equation. This phi here is now an n cross n matrix. Okay, and that is why we could actually do it that way. So, what does it satisfy? Well, this initial condition is identity, that is what we said, that the phi actually has an initial condition identity, and therefore, x of t is phi t comma t 0 with x of 0 is actually the solution of x dot t is a t x t. Right. So, this is where the matrix differential equation comes from, and that is also the reason why I am actually doing this ugly looking series very explicitly, right, just to show you the relation with the matrix differential equation. Now, you can write this entirely for the LTI case, x dot equal to a x, right, and just do the substitutions. I will not I will possibly skip those, and you can just verify of how this Pino-Baker formula holds for the LTI case. I will just as an exercise, right, just verify the Pino-Baker formula for the LTI case. Okay, the results won't be surprising, but yes, it would be easy, or it would be helpful just if you write down the details for yourself, just to kind of get concepts ingrained into your mind. Okay, but I do not want to do this kind of integrals all the time, right? Now, are there easier ways to find this? Well, it turns out that we can do something nice here, right? So, again, let us start with the LTV, the linear time varying equation. X dot is Ax, with A being time varying, and let me start with n linearly independent initial conditions. Okay, and that is the reason why I am actually doing this. Okay. So, with each initial condition I will have a certain solution, right. So, let me denote those solutions starting from initial condition, say x1 t0 as x1 t, the solution starting from xn t naught as xn of t, right, and let me have n different solutions. Okay. And as a consequence, if I differentiate this, what I have is x dot is of course the differentiation of each of this. Now, what does x1 dot satisfy? X1 dot with an initial condition x1 at t naught is also a solution of this equation. So, I will have A t x1 t. Similarly, for any I, xi dot of t is A t xi of t. Okay. And therefore, I can write this as again some kind of a matrix differential equation, right. So, x dot of t, which is x is now an n cross n matrix, is A t x t. So, I am just combining these solutions, right. Okay. Now, well, a key here is that this x1 t naught till xn t naught, the n initial conditions which I choose must be linearly independent. I will shortly tell you why that is important. So, because of that, we have now a matrix differential equation, and okay, if x of t naught, because I assume that these are n linearly independent conditions. So, this will turn out that x at t0, which is essentially this vector, right. If I just write down x of t naught is just this, or in fact this matrix collection of all these vectors x1 t naught till x1 t naught. Okay. If this matrix is non-singular, then well, what I call xt, I call it as the fundamental matrix. Okay. So, the reason I also say that it is actually not unique, because I can choose any different set of n conditions, and that will give me let us say I choose say x n plus 1 t naught till x twice of n t naught, which is whatever initial condition in the state space, that will give me different set of capital X, and that will lead me to a different set of a fundamental matrix. So, I call this a fundamental matrix, but this is not always, or this is not unique, it need not be unique. Okay. So, the first thing, okay, let us see of why. So, if I start with linearly independent initial conditions, so my claim is that x of t is non-singular for all t, right. The fundamental matrix, if I start with linearly independent conditions, then this matrix is non-singular, which means it is it is invertible, its determinant is non-zero, and so on. Okay, let us see how we will do this. Okay, even though it said prove this, I think I actually proved it here. So, let us start with this matrix xt, and let us do the proof by contradiction. Let us assume that it is actually singular at some time value t1, okay, which also means that there will be a vector, a non-zero vector, such that x at t1 times v will be equal to 0. Okay. Now, given this x at some other time t, which is not equal to t1, I can always construct a vector small x of t as this capital X of t times this v and this v can be the same, they are like non-zero. Okay. Now, if I compute the value of this small x at t1, what is small x at t1 is capital X at t1 times b, this actually is equal to 0. Okay. If x of t1 is equal to 0, then x of t equal to 0 for all time t in R, right. What does it imply? That x of t0 is equal to 0, which is a contradiction, right. And therefore, we can prove that or we can show that x of t is non-singular for all t. Okay, which essentially means that if x of t naught equal to 0, I start with 0 initial conditions, I just end up with the solution being also staying at 0, and that is not very interesting to me. So, this is an example which we started with. So, let us see if we could find the fundamental matrix of the system using two initial conditions 1 comma 0 and 1 comma 2. Okay, do not really confuse it with that I am having a 0 initial condition. Well, this is actually a non-zero initial condition because both vectors are not 0, both initial conditions are not 0. Okay. So, the first one we could compute, and okay, again all the steps are exactly the same that we did earlier, and therefore, I can say that the fundamental matrix is given by an expression like this. Okay. This is straightforward consequence of what we started off the lecture with by defining an example. You can check that this is of a full rank because the determinant is 2 for all times t. Okay. Now, how do we construct a state transition matrix of LTV system starting from this definition of the fundamental matrix? So, the claim here is that start with any fundamental matrix of x dot equal to a times t times x, then the state transition matrix is simply x of t, x inverse of t0. Okay, which also eliminates the thing that okay, I am not really looking at any 0 initial condition, that is not really exciting to me. Now, this phi t comma t0 is called the state transition matrix of a t times x. Okay, as usual, we will have to verify this claim, right. So, can I show that, well, that the state transition matrix is also a unique solution of this one. Okay. In the previous lecture, we tried to verify how the state transition matrix is actually a solution to the matrix differential equation and also to the vector differential equation. Again, one is by checking the initial condition, and second also that the solution must satisfy the actual differential equation. Okay. So, let us first say that okay, is this a solution to my differential equation. So, first just verify what happens phi at t0 comma t0, I have x at t0 and x inverse at t0. So, I have the identity. Okay. Second thing is, okay, let me check what happens with phi dot. Phi dot is x dot of t with x inverse of t0 what is x dot? X dot was a x t x inverse of t naught. Well, this is nothing but a. So, x t times x inverse is again phi t comma t0, right. So, this actually is solution. The uniqueness is guaranteed. Well, we assumed that we know that uniqueness is guaranteed. I will not verify those so called Lipschitz kind of conditions, we will not complicate our lives. So, we just assume that God has given us all the equations for which there is a unique solution, right. So, let us make our life simple for the time being. We can dig deeper a little later in the course. Okay. So, this is nice here, right. So, this actually is the solution to the differential equation. Okay. So, few properties which well, we can also take you from yesterday's thing, right. So, show that okay, this is easy to show. We proved these two properties yesterday in the LTI case, but the proof will kind of be the same or just follow the similar patterns, right. So the first one is trivial, the second one is also easy to show, the third one you just say that well these are two equal functions, so just check what happens to them at some initial conditions at say t naught comma t naught, and then just satisfies and just check if 3 satisfies the same differential equation, then the two functions are the same. Okay. So, okay, let us just at least check the initial condition, right. T naught comma T naught is phi T naught T1 phi T1 comma T0. Okay, so if you use just the previous property, this is the inverse, this is phi inverse, so I just have the identity, and I can still just look at the differentiation of this and claim or easily verify that they satisfy the same differential equation. We have done enough of those steps, so I will leave that as an exercise for you. Okay, you can just also use this specific form of solution just to make the proof a little easier. Okay, as an illustration, let us recollect the example that we started with, where x dot was 0 0 0 t0 x of t, and we wish to find the state transition matrix of the time varying system given by this A matrix. So, we earlier computed the fundamental matrix to be of this form a couple of slides ago. To compute the state transition matrix would just be application of this formula, right. Phi t t0 is xt inverse of t0, and if I just used the definitions, it just turns out to be that this matrix over here is my state transition matrix for the given system. Okay, so that's a straightforward procedure to compute the state transition matrix of a linear time varying system. Okay, so the obvious way to look at it is, again it's a simple extension, and much of the steps here will be similar to the previous lecture, right, when we were looking at forced LTI systems. Okay, so most of the things remain the same, right. So we claim that the solution to this forced LTV equation, where now B is also varying with time, is just given by this expression. Okay, so you can just do these steps and arrive at this, right. And again, phi t comma t0 denotes the state transition matrix of the system A x dot equal to AT times x. Okay, so again the way we verified yesterday, making use of the Leibniz rule, we can still verify using exactly the same procedure, just that in that case this phi was e power a t minus tau. Now I have a little more general phi, but nothing really changes in those steps, right. So you just verify just by differentiating both sides, and you can say that you can actually realize these two, that x of t actually satisfies this differential equation. Again, the steps are skipped for obvious reasons, and I would really want you to work out few of these things by yourself to get those concepts ingrained into your mind. So once I know x once I know the solution, I can always compute what is the output. That is again a very straightforward extension of things that we have been talking so far. So the last topic of today would be how do I handle systems which are discrete time and also varying discrete time LTV systems. So the model would be the same, right. So just that A would now be depending on k. So the aim is to find solution xk given certain initial condition and some input. So the steps are again similar. So we define an equivalent notion of a state transition matrix for the discrete time case. So the steps all remain the same, right. So I have discrete. So the state transition matrix is a solution of this matrix differential equation. Okay, and with solution being of this form, it is a little easier for me to compute the closed form expression in the discrete time, as was also little easier in the continuous time. Where we had was, it was all higher powers of k. You can also realize that condition here, right. So, if all these a's are constant, you just have a power k. Okay. So I did not really write down things too explicitly, so or maybe just for see, if I have x k plus 1 is a k x k. Okay. So what happens when k equal to 1? X of 1 is a of 1 x, sorry, a of 0 x of 0. Similarly, x of 2 is a of 1 x of 1. This is a at 1. What is x of 1? Is a 0 x 0. So, this will be a 1 times a 0 times x 0, or here I just call it as k 1, k naught and k naught and so on, right. So, that is little easier to verify than in the continuous time case. Okay. So, the properties again will translate very nicely from the continuous time case to the discrete time case of what is the identity and so on. The only thing we could encounter, and we will talk about this explicitly while we are talking of controllability of discrete time systems, is that this matrix A times k, A of k can sometimes be singular, and therefore, the phi inverse may not be necessarily defined all the time. Okay, we will postpone this discussion when we actually encounter a situation like this, whereas all the other cases actually remain the same. All the other properties of the state transition matrix remain actually the same. Okay. So, similarly, if I have input, so I just augment my solution with the input terms, right. So, and similarly I can compute the output. So, just straightforward exercise here once you have understood the continuous time case. So, to conclude, so we started this lecture by looking at solutions to LTV systems, and we actually made a nice justification to why we used a matrix differential equation as a basic building block to compute what is called the state transition matrix, and we also looked at towards the end discrete time LTV systems. So, this concludes week 4. Starting week 5, we will look at different kinds of equilibrium points of systems, both from the linear and the nonlinear case, and then motivate our case towards linearization of nonlinear systems, and what are the properties that are retained and what are the properties that may not necessarily be retained while we do the linearization procedure. Is there only one way of doing linearization, or there are multiple ways? So, all this will be covered in next week's lecture. Thank you.